Okay, this is the last video of this semester. I am so happy. Uh, so we are near the end. Oh, okay. Now I'm going to think about the education and wage example again. So you remember the horizontal axis is education, years of education, and the vertical axis is hourly wage, right? So these are the result, OLS result. So this minimizes the sum of squares. So now you understand what they mean. So the sum of squares, so the total, let me put it like this. So the original variation in the hourly wage is about 74,000 variation, right? Variation was 74,000, but your regression model, the education could explain only 7,000, less than 8,000. And actually, most of the hourly wage was not explained. So let me increase the font size. So, right, out of 74,000, 66,000 are not explained by your regression model, right? That is not that these are not that good, right? Not a good explanation power. So as a result, the R square also increase sample size. The R square is only 10%, right? It's like 10.59%, right? So R square is pretty small. So then let's think about what is the problem. Okay, uh, like we would like to explain the wage, hourly wage, how hourly wage is determined. And we use education as a variable to explain how wage is determined. But actually, think about the reality. Your wage is function of a lot of factors, right? It's not only about your education. Your education helps, like changes, affects your wage, but there are a lot more things that comes into play, right? Your GPA and also which school you went to and what is your major and your work experience and your personality, even your characteristic, your personality. And also there is a kind of luck and like your a lot of things matter, right? So wage you as an economist you should understand that wage is not easy to explain, right? If you think about that, then 10% is actually pretty high. One factor explains 10% of your wage, right? So in that sense, it's kind of too high, I think, right? Okay, yeah, so it's subjective decision. I'm not saying it is right or wrong. There is no clear, you know, decision whether it is wrong or it is right. But anyhow, you know the problem. Wage depends on a lot of factors, and many of them are not in your data. So all of these unobserved factors are just part of the error term. So the standard error is pretty high, like 5.4 when the right. So the standard error is pretty high because a lot of factors are not included in your analysis. Okay, so then the solution is that how can we handle that? The idea is include more variables. We have to include if the unobserved factors are actually observed, then we can do a better job. That is a very simple idea. Like so, as I included another variable, age. So so let me change the name of salary, like wage, to salary because they may be confusing. So I'd like to explain salary, hourly pay. I will explain this hourly pay using education and your age. How old you are. So if you are older, that means you have more work experience. So maybe your experience will help your productivity, of course. So your you will get higher pay. So let's see what happens when you explain the wage using two variables now. So idea is the same. We are going to use data, data tab, data analysis, and regression, and choose Y. The output is now hourly pay. And for X variable, you have to include two columns, right? And everything being the same, click OK. So we have two scatter plots because you cannot draw three variables in one scatter plot because we only have two dimensions here. So one is age versus hourly pay, and the other is education versus hourly pay. But this now then scatter plot is not that helpful because your predicted salary depends on your age and your education at the same time, so it is not a line anymore. So if you had three-dimensional scatter plot, it could be a line like flat, plain, like plain, but when you have more than two variables, the scatter plots are not that helpful to visualize what's going on. But at least education has still pretty strong relationship, like pretty linear, right? You see the red are the predictive ones, but age does not help that much, right? Even though you are at the same age, sometimes your predicted salary goes below zero, so not that helpful because this is a limitation of two-dimensional presentation, okay? But still, our output tables are similar to what we used to have, right? So these are the coefficient estimators, point estimators. Now we have three estimators, beta 0, beta 1, and beta 2. So the first one is the intercept, and the second one is the slope of the coefficient of age, and the third one is the coefficient of education, right? So, and we have their standard errors, t-stat p-value, confidence intervals, and sum of squared, residual sum of squared, like regression sum of squares, and total sum of squares, as before. And we have just like R squares, standard error, number of observations, as before. They are the same thing, right? Same guys. Okay, so the idea is simple. The motivation is we would like to use as many variables as possible because there are a lot of factors that affect the wage, and technically speaking, you have to include all those factors to better explain the hourly wage. And then the model becomes like that. We call this multiple regression as opposed to simple regression, single regression. So in single regression, you have only one independent variable, one x. But now, actually, you have multiple x variables, right? So I have only two variables, but you can extend even more. And then when you include more variables, you have to be careful when you interpret beta 1. So beta 1 must be interpreted as the effect of x1 when x1 increases, y increases by beta 1. But you have to keep this in mind while x2 is being fixed, right? So beta 1 is the effect of x1 on y when all the other variables are constant, right? That's the important condition when you interpret the slope. Otherwise, interpretations are pretty much the same. Beta 0 is the value of y when x1 equals to 0 and x2 equals to 0. So intercept is the same thing. And fitted value is calculated in the same way. Just plug in your estimated value and ignore the error because error is not predictable. So ignore the error and plug in the estimated values, then you get the fitted value. The residual calculated in the same way after you calculate the predicted value. You can calculate the residual by comparing the predicted outcome to the actual outcome. And then, based on those residuals, you minimize the residual to obtain beta zeros, right? So estimation of beta 0 and beta 1, beta 2 have the same idea, minimizing the sum of residual squared, okay? Also, R squared is calculated in the same way by comparing the variation of how much you the variation in the original observations versus the variation you fail to explain. So everything goes the same afterwards. Okay. So and then that means it does not matter you include more x variables. You can include more variables, and in like research, in actual research, we use like say 10 variables, 20 variables. That is not that many, right? Like sometimes the number of variables can be like 100, 200. So that's also possible because as your data get better, you have to use them better. So multiple regression is a simple extension of simple regression. Okay, then you can predict a wage like this, like you can predict a wage for a person who is 30 years old with 4-year college graduation. Then using those numbers, try to calculate the predicted wage for this guy. So simple algebra, simple computation. So pause the video to do the algebra, and then the answer goes like this. So intercept and beta 1 times age, but age was assumed to be 30 years old, and the person was 16 years educated. Right? The education is 16, and you multiply the corresponding coefficients to age and education, that is 10. So this person, 30 years old with college degree, is expected to earn $10 per hour on average, approximately. Okay. And then now, what are the statistically significant variables in this case? Another thing you have to check here is whether your regression model is meaningful or useless, right? We are worried about if our variables are not explaining the wage at all. So that is our concern. Then what are statistically significant variables? Actually, you have everything here. You can just look at those t-stat and p-value. It is a hypothesis testing. Okay, the answer is, remember, this is a hypothesis testing, but the null hypothesis is the slope equals to 0, right? So if the slope equals to 0, that means that variable is useless in explaining your wage. So we would like to reject it for our regression model to be meaningful. So we hope to reject. Then if we could reject it, then we say the variable is significant. In this case, if you look at the t-statistic, if the t-statistic is different from 0, then we are going to reject the null hypothesis, which is good for you, right? So education is 16 and age is only like minus 1.2. But remember, at 5%, the threshold is 1.96. So if the t-statistic is within plus minus 1.96, then your null hypothesis is not rejected, which means your variable is not explaining anything, right? So age is in between plus minus 1.96. So age does not explain your salary. Your hourly salary is not explained by age. But education has a huge t-statistic, which is good for you because the null hypothesis is rejected. So education is helpful, is an important variable explaining a wage. So the answer is C, right? So education is important to explain wage, but age isn't. This is another interesting point. So when you include many variables, some of them may be useless. Actually does not do anything. In this example, age is not statistically significant, right? So even though the estimated coefficient is minus 0.048, but this could be just a random error. Actually, age is irrelevant, but because of random error, you get minus 0.04, too small. That's what we can say. And then also that is reflective to the R square. Only with education, when there is only one variable, it explained 10%. But now, after including age, R square is still 10%, 10.6%. So R squared did not increase. The explanation power is the same as before after including additional variable. So that's another reason why age is not statistically significant. So it does not help. Age does not help. However, the coefficient actually changed a little bit. The coefficient when you like without age and with age, the coefficient of education coefficient changes, but that change is very small. Again, that's because age, the effect of age on wage is really small, but it has effect. So you have to recalculate everything, but the difference is not that big. That's what happens when you include additional variable. In this case, I would recommend using only one variable, right? Only one variable, using one variable would be better, right? Yes. Okay, so this is the end of the main part and the last example. As our last example, I want to show you a very interesting example. Ice cream and intelligence. The Economist, the famous journal, The Economist reported that ice cream induces anti-brain freeze. So it makes you smarter, which is evidenced by the relationship between ice cream consumption on the vertical axis and standardized reading score, test score across countries, right? Different countries have different reading scores, and it is very strongly correlated with ice cream consumption per capita, of course. By the way, so the regression model used here is actually nonlinear regression. It's slightly curved. That is simple generalization of linear regression model. But for now, that's not that important. And what's interesting is, surprisingly, the R square is 49%. So it's interesting. Ice cream consumption explains 49% of your reading score, right? So if you so your reading score is half of your reading score is related to ice cream consumption. What is it? How can you explain that? Right? It is, by the way, it's not kidding. I'm copying the Economist, right? It's a column from the Economist, right? You can find the actual column from here. Okay? Okay, of course, this is a joke. The Economist is trying to fool you. Actually, this is published on the April Fool's Day in 2016. So this is not true. What I wanted to say is that regression does not guarantee causality, right? Earlier, in our earlier example, I said as if the wage is determined by education and the cost is determined by your production. In those cases, I just said it's determined by y is determined by x because it's obvious. It's just obvious, not from statistics. So economically or intuitively, of course, your cost depends on is determined by how much you produce, and your wage obviously is determined by your education. So it is too obvious. So I just explained that way. But in some cases, it's not that obvious, like this. Reading score and ice cream consumption. We don't know why. There is no clear reason ice cream consumption determines your reading score. There is no cause and effect relationship. Then the correct interpretation is so the countries that consume more ice cream are more likely to be economically developed. And more economically developed countries tend to have higher reading scores. So the relationship is not direct, even though the relationship is pretty strong, right? The R square is nearly half, but it does not have any meaning. Just like you can just totally irrelevant variable may have a strong relationship, may look like having a strong relationship, but that does not mean anything. So like last week, I saw a very interesting news. Actually, I'm recording this before the presidential election. So last week, I saw an interesting news from CNBC saying that a price of tomato is a good predictor for the presidential election. All right. So of course, statistically, price of tomatoes could be correlated with the previous presidential election results, but there is no explanation behind it. What's the matter of tomato to presidential election? So the point here I wanted to say here is regression and statistics is just a tool, but in the end it is you who have to interpret the results and who have to correctly use the methods, right? So you should be careful not to overinterpret or mislead the results. So I just wanted to show the lesson with an interesting example previously. And another thing here is it's related to chapter 11. We only learned linear relationship. So basically, I assume that the trend line is straight line. It could be not true if you have a nonlinear relationship like this. The relationship is not linear, right? Because the slope increases, right? Another famous example is GDP and pollution, right? When a company starts to develop, then pollution increases. So when GDP increases, pollution increases in the beginning, but at a certain point, the country starts to take care of the pollution. So even though the country keeps growing, the pollution goes down, right? That is so-called Kuznets curve. The famous economist, the old economist Kuznets, found this kind of relationship, right? Like equality is similar. Equality, like income inequality increases when a country starts to develop, but then the country tries to minimize the income inequality when it is sufficiently developed. So many of the variables have nonlinear relationship, right? So you have to be careful when you apply linear regression because your straight trend line can be misleading when there is a nonlinear relationship. So that's another word of caution that I wanted to tell you. Okay, thank you for watching the video and thanks for your work throughout the semester. And if you have any questions, I'm here to help you. And I provide after service if you have any data problem from any other courses in the future, next semester, next year. I would be happy to help you, right? So if you're interested in any research and any data work, data analysis, let me know. I'll be happy to help you. Okay, thanks. Have a nice winter break and have a nice holidays and good luck with your remainder of your life. Bye. See you later.